executable is going to call. The compiler is responsible for generating code, which is going to call some value from that table. It's going to like generate code that reads a value from the table and then calls to that. And in reality, then the linker also has a hand in fixing that up, because when you combine together multiple things, all of their import address tables are going to be combined together. And so the linker potentially modifies this code a little bit as well. Okay, well, it says to show imports in view, but it's too early for that. So we started back here at the optional header, and we said all of this array right here is the data directory. And so we're specifically going to be looking at this directory entry import. This is index 1 into the data directory. We said each of these elements in the data directory, they're all just, hard-coded. There's 16 array. There's 16 of these image data directory structures, all in an array, all in the optional header. And so for this index 1, we have, as usual, all of these are going to have the same format. They're all going to have a virtual address pointing at some other data structure and a size. And again, the virtual address is a relative virtual address. So it's just saying, here's some offset from the beginning of the file in memory where you can find the information about imported functions. All right, so once we go to that offset, what we're going to see is the image import descriptor. So this is a sort of fairly overloaded thing. You can see that it's got a union as its first thing. But yeah. So in terms of this initial union that it has, we're only going to care about this original first func thing. And then the second thing I should say about that, since this is not a named union like that previous one we saw. Previously it was misc.virtualSize, right? Because the union itself was named misc. This has no name. And therefore, literally, you could just, access characteristics or access original first func, and it's accessing the same initial 4 bytes. But we're only ever going to be accessing this original first func field. Yeah, and that's not pointing at the right spot. But I think your version is correct. So that should be pointing at... So yeah, and then I also highlighted. So all this comments. This is from winnt.h. So all the comments are their comments, not mine. But the first comment we're going to care about is this time date stamp. We're not going to care about the field, but we're going to care that by default, this is in the common case we're going to be looking at first. This is always going to be 0. Later on, we'll move to the case where it's -1, and we'll never actually see this third case. So literally, this time date stamp is never going to be a time date stamp in the cases we're concerned with. It'll either be 0 or it'll be -1. And the forward chain is always going to be -1 as far as we're concerned. Well, not always, as far as we're concerned for this initial example. And then there's going to be a name and a first func. So, all right, the original first func is a, quote, badly named field within the import descriptor. And what it is an RVA of the import names table. So there's going to be a table that's going to have pointers to a bunch of strings. Each of those strings is the name of an imported function. So if you import printf, there's going to be a table somewhere that has a pointer to the string printf. All right? So actually, but so it's not a direct pointer, unfortunately. It's by way of it points at a table of these image thunk data structures. So the reason why it's called original first thunk is because it's actually pointing at these image thunk data structures, which we'll see in a second. But for right now, all you need to know is original first thunk is the thing which eventually gets us to that import names table, which is the table that has all the strings of what your imported functions are. First thunk, on the other hand, is the thing which is eventually going to get us the thing which is originally going to get us into the import address table. So this is that table of function pointers to the function. So there's going to be one table of strings that say the name of the function, and there's going to be another table of actual function pointer addresses. So these are the actual locations in memory where you need to start executing if you want to do printf or whatever else. Let's see. And then name is an RVA which points at a string for the module that you're actually importing from right now. So if you're importing from libc, this particular descriptor, so this is a descriptor where there's one of these descriptors per module that you're importing from. So if I import from, MS, whatever it's called, mscrt.dll, Microsoft C runtime.dll, if I'm importing from that, there's going to be one of these that says, okay, the name is mscrt.dll, and here's the pointer to the address of function addresses that I want to import. Here's the pointer to the names of all those functions. And then you move down, and there'll be another one of these descriptors that is for, kernel32.dll, and another one that's for ntdll.dll and stuff like that. So the point is, each of these descriptors, there's going to be an array of these descriptors, one per module that you're importing from. So that's why, we have the size field again back here. The virtual address points at one of those descriptors, but there's going to be, however many of those descriptors, 2 or 3 or 5 or however many. And the size will tell you, take the size of one of those descriptors and divide size by the size of one of those descriptors to say, here's how many structs I have all in an array. So we'll get to pictures here in a second. See how far from pictures. Okay. All right, so bear with me while I try to get us the pictures as quickly as possible. So we said that the first thunk and the original thunk, each of those actually points at some data structures called image thunk data, and it's going to point at an array of those structures. And so these image thunk data, it's actually, each image thunk data is really just one D word in a union. So each of these structures is just a single D word, but it's a union. And therefore, there's like 4 possible interpretations. And one of those possible interpretations, what this picture is trying to show is one of those possible interpretations points at this other type of structure called an image import by name structure. But we don't care about that yet. There's basically 2 dueling interpretations of these image thunk data structures. So, like I said, one of these, so the original first thunk points at the names table. And the names table is typically going to interpret this image thunk data as an address of table. And the first thunk points at, again, these image thunk data structures. But that's pretty much, well, that will eventually always consider this structure like a function. So, yeah. Really, I just want to get to the picture. So we're going to go to the picture, and then we'll come back. All right. So this is roughly speaking how things are going to go within these data structures. So you've got your data directory entry, and that says, here's the start of all of my import information. The thing it points at is one of these image import descriptor data structures, which has original first thunk, time-based stamp, which we don't care about, forwarded chain we don't care about, name and first thunk. So there's 5 fields in each of those structures. And you've got some array of those structures, typically terminated with a all null entry. So here we're saying, there's 2 of these structures, one of which points at NTOS kernel imported information, and one of which is just the terminating null thing. All right, so here, this information right here is going to be sort of assuming that we're looking at the import information for some kernel driver. Specifically, I think it's null.sys. So that's why it's importing an exe here. It's importing NTOS kernel because that's the main kernel of Windows. And so it's saying I have null.sys, which is just some kernel driver, and it imports some functions from the main kernel. Specifically, some of those functions are io-delete symbolic link, RTL, init Unicode string, etc. So there's going to be some large array of these. But when we're actually parsing the image import descriptor, what we have to do is, in order to find the names of the functions which are being imported, we can actually start at either of these, but we'll pretend we'll always start at original first thunk. And so this thing is an RVA, original first thunk is an RVA of an array of these image thunk data structures. And so the image thunk data was that heavily overloaded 4 possible interpretations within a union. So each of these is just a single D word, but it has like those 4 possible interpretations right there, right? So this array is an array of D words, but we could call it forwarder string or function or ordinal or address of data. Yes?
64-bit.
64-bit will basically just have slightly different, so you can see here I have 32 on here. There's just going to be actually type defs where you would use like image thunk data, but if it's 64-bit, it would type def it over to image thunk data 64. So it'll be slightly different, but it's mostly the same. It's mostly different sizes, I believe. I haven't looked at the 64-bit that much, though. So this points at an array of those D words where each of them can have 4 possible interpretations. Now, for the import names table, it always is going to have 1 interpretation and 1 interpretation only. It's always going to be interpreted as address of data. And the thing is, if it's interpreted as address of data, that means that address of data is a pointer to an image import by name structure. And that's what that middle thing in the columns were. So, we didn't talk about the image import by name structure because I was trying to skip ahead, but this is basically what the image import by name structure looks like. It is initially a hint field, which is a word. It's 2-byte field. And then it has, it calls it byte and name, but in reality this is just trying to say that there's some variable sized name, some array of bytes after the hint thing, where this is the actual literal string, basically. So you'd have 2 bytes where it's a hint, and we don't know what a hint is yet. And then we have X many bytes where it's actually, the printf string or, the IO, whatever that thing requested, IO delete symbolic link. So what I'm trying to show with this picture here is, for the import names table, we always treat it like it's a pointer to this other structure, image import by name. And what that is it's 2 bytes initially, called the hint, and then it's however many bytes it takes to name the actual function which you're importing. So this is where you find the actual name of the function which is being imported. All right. And so this is always the interpretation for the imports names table. Now, we can see over here there's that first thunk, and I said that's supposed to be pointing eventually to all the function pointers. The thing is, when it's on disk, so I have 2 different pictures here. I have on disk versus in memory. On disk, the import address table points to the exact same data that the import names table does. So on disk, they're just both pointing to these structures that have a hint and a string. In memory, this import address table gets filled in with the real function pointer addresses, but that's the OS loader's job, basically. So that's the OS loader goes through. It goes to each of these import descriptors and say, oh, I see you're looking for something from ntus kernel.exe. What are you looking for? I'm going to go to your import names table. It looks like you're looking for IO delete symbolic link. Oh, I'll go find the address of IO delete symbolic link, and I'll stick it into your import address table. Right? So this is sort of the, this is where there becomes a difference between these 2 things. So the reason you need to know this is because on disk, if you ever look at the, if you look at the data structure on disk, like we're going to do in a second, you'll see that they're both pointing at the same data. But if you look at it in memory, you'll see that only the import names table is pointing at these structures with strings, and the import address table will be pointing at the real functions. All right. So now I just need to say what that hint thing was quick. So for that image import name where it's just like a hint and then a string, the hint is basically an ordinal, which is like an index into the array of exported functions. So if something's exporting a bunch of functions, this hint can be basically telling the OS loader, oh, you're looking for, IO delete symbolic link. Go to ntus kernel's export table and go to, index 14b, and that's probably where you'll find IO delete symbolic link. It may not be the case. That's why it's just a hint, right? So it's telling it start here, and if you don't find it there, then go do some other stuff. But for right now, well, the other stuff would be start searching the exports table for this specific string, IO delete symbolic link. So we're going to look at this quick in P view, but are there any questions? I mean, I know I went through this 1 fast, 2 is after lunch, 3, it's like 3 or 4 levels of indirection through data structures like bam, 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 bam. But would anyone like to ask me a question reiterating your current understanding and asking me if that's right? Or anyone just have a question, generally speaking, on what's going on here with this names table and import address table, and how, original first thunk just finds the names table, or just first thunk finds the address table. Any questions? Yes.
I'll try reiterating because I don't think I really understand.
Okay.
I think what you're saying is that we have on disk we have the original first thunk and the first thunk in this image import descriptor.
Right.
And on disk they both point at the same thing because the addresses aren't resolved until we link them, or until the loader actually finds where those modules are and loads them into this program's virtual memory.
Yep.
And then the program can look up functions by name and resolve them somehow into the address because the original first thunk.
The OS loader, yes. So almost right.
Can resolve by name because on disk, the original first thunk and the first thunk are both, or each image thunk data in each of those arrays points at the same thing to start with.
Right.
And since they're indexed the same, the OS loader can
functionally
where to point each of the address table.
Right. I believe what the OS loader actually does is just read the import names table. In reality, this import address table doesn't have to have any values to start with, as long as your import names table is right. So the import address table could be filled in with all zeros, and the OS loader would still know, go to the import names table, and yes, for the index 0 in the import names table, go find that function pointer, go find that address of the function, and stick that into index 0 in the address table. For index 1, go find the specific offset in NTOS kernel where RT init Unicode string is, find that absolute virtual address, and stick that absolute virtual address into the image address table, basically. So it's because of all this, recursive, all of this recursive dependencies and requirements for importing from one module may request another module, that none of this can be, well, it's not that it can't be resolved at link time. It can and it will, and we'll see that as the next example. But generally speaking, the point here is, for those DLLs, we said they have a preferred address that they're going to get loaded into memory, but they might not get that preferred address. So if they get moved around, the address of IO delete symbolic link may not be the address that you thought it should be. So it's the OS loader's responsibility to say, for every function which this executable needs to run, I need to go find, when I actually map everything into memory, I need to go find where that real function address is, based on whatever it's saying about the exports from, whatever library or NTOS kernel. So, yes, you're basically correct. Yeah. So let's play around with this a little bit in PE view now. So on your desktop, you should have an executable called PE view. So it looks like a magnifying glass. Go ahead and open that up. Then it's going to ask you what you want to open, just so that we can see exactly what that picture was based on. I want you to open C:, Windows, System 32. Drivers. Null.sys. So that's what we based our picture on. So C:, Windows 32, or sorry, Windows System 32, drivers, null.sys. Then go ahead and open that up. All right, so we haven't played with this yet. So before we jump right to the imports, let's kind of browse around in some of the other stuff we saw first. So if you click on image DOS header, right, you'll see the stuff that we talked about. You'll see the signature, the MZ. And actually, even if you just click on null.sys first. So null.sys, this right now is just like a raw hex dump sort of view of it. So this is just the raw bytes of the entire thing. There's some structural definition within this, and PEView is the one who's going to, help us understand that structures. So we can see initially there's like an MZ there, and then there's other stuff. There's a question? Yeah.
Yeah, there's no question. I thought the very first field was supposed to be a 4 byte.
You're thinking of the first field in image NT header, the signature.
Yes, I am.
Yep. So we always start with the DOS header. The DOS header's ELFA new, which was that last field, that tells us the offset to the NT header, which is there where the PE is. So, yep. Starts with the DOS header, then becomes a PE header. So yeah, if we, look at the raw null.sys, we can actually see something interesting here. One, we have the MZ to start with, but there's actually this little string here. This program cannot be run in DOS mode. Immediately after the DOS header, there's actually this small little stub program. So this is a valid DOS program where all it does is print out this program cannot be run in DOS. So this is a Windows program. It can't run in DOS, but they tacked on a little DOS program so that, for backwards compatibility, when they first moved from DOS to Windows, people would have gotten confused about like trying to run their Windows programs in DOS, right? So they hacked into the headers between the DOS header and the PE header, the NT header. Between that, there's a little fully functional DOS program that's, when you run it, it just prints out this program cannot be run in DOS. So we could like disassemble this if we want, but not from within this tool. So, all right. So anyways, we start with the DOS header. You can look at the other values if you want. You can see most of them are 0 here. Some of them are non-zero, so a bunch of them are reserved. But the main thing we cared about, right, was that last field, and that said at offset hex D0 into this file offset hex D0, there's going to be an NT header. And so what PEView is just doing is it's going to offset hex D0, and it's interpreting it as PE header. And so this is file offset D0. This is the raw data. But when it starts interpreting it, it says at offset D0, there's the signature, which is 0000 EP, because it's in little endian order. And then there's the file header and the optional header, right? So we can look at each of these and see various data. The first thing that we care about is that time date stamp, right? So inside, so if you want to find the time date stamp for a file, if you were trying to like write your own little program just to like quickly, pull out time date stamps, for instance, you just need to know, okay, well, first I need to know what a DOS header looks like. I read the last field of the DOS header. I jump to that offset in the file, and then it looks like an NT header. What does an NT header look like? It has a signature, then a file header, then an optional header, right? So you could then just find the file header, find the right offset into it, and then you'd find the time date stamp. So this shows that my null.sys was actually compiled in 2001. So they haven't needed to update null.sys in a long time. I think some of the other stuff like Notepad is like 2008 maybe, but yeah, it's sometimes funny to look at stuff. I mean, yes, this didn't, it's a null driver. It doesn't really do anything, so it hasn't needed to be updated. All right, so there's that. Here's the characteristics, which again, PEView is being nice for you. It's pulling out thick fields. These are, bitwise ORed together. So the literal characteristics is 10E, right? But it's a series of bitwise masked things. So it says it's an executable image. It says line numbers are stripped. Local symbols are stripped. And it's a 32-bit thing. So, okay. Whatever. Let's see. What else we got here? Positive optional header we don't care about. Number of sections. There it is. 6. Number of sections. So this right here, what it's showing on the side, this .art data, .data, page, init, resource, reloc. These are my 6 headers to the side here. Immediately after the NT header, right? NT header, and then section header, section header, section header, section header, section header, section header. And PEView knows to interpret this as being 6 of them because it looked in the file header and it said there's 6 for the number of headers. Moving on to optional header, right? Just a quick point out, the stuff we already talked about. Address of entry point, you can see that's not some full virtual address, right? It wouldn't make any sense to be jumping to just address 59A. So this is a relative offset from the beginning of null.sys. It says the first chunk of code that I want the OS loader to start executing is null.sys is base address plus 59A. And we got things like image base. Well, I can, like I said before, actually, the OS loader doesn't care what kernel drivers ask for image base. It'll give it an image base wherever it feels like. And then we got stuff like this major OS. We didn't care about this in terms of what we saw, but this is Windows XP is like 5.1. Size of image. That was that total size of the entire thing, right? Optional header dot size of image. This is saying if you're going to map null.sys into memory, you better allocate at least B80 bytes worth of memory. DLL characteristics. This one actually has no characteristics, which is interesting. All right, but then down at the very bottom, this is where each of those 16 data directory entries are. They're, like I said, they're embedded into the optional header structure. So they're just, RVA size, RVA size, RVA size. And it knows that, the first one is export 1 because they had those macros that say, the export index is 0, the import index is 1, debug index is whatever it is. So each of these, you can see some of them are zeroed, some of them are filled in. So for instance, null.sys has nothing for its RVA for exports. That means null.sys exports no functions. But what we really care about is this import table, right? So we're trying to dig through and find how the OS loader actually finds the imported functions here. So what it would do is the OS loader would go down to this data directory table. It would go to index 1, which is this import thing, and it would say, okay, at relative offset 610, hex 610, in this file, or in memory, rather. So the OS loader would basically come into the data directory, and it would say, okay, I'm going to go to the imports one. It's going to say, relative offset 610 into this file, there should be one of those image import descriptors, right? So that was the one that had all the comments with it. So if I want to actually find that, so this is where it kind of breaks down in terms of it parsing stuff for you. So if I I could expand each of these sections. And basically what I'm going to do is I'm going to look for one that's called import directory table right here. And what this is basically it's the those image import descriptors. But we can see that this makes sense because when I click on when I click on image import directory table, when I click on that, I can see over here that it says p file 610. So that's like telling me it's 610 into the file. It's also up here at the top, there's these 4 little arrow boxes right here. This one says file offset. This one says view offset. This one says RVA. And this one says VA. If I click on, for instance, RVA, right now the RVA will be the same. It's trying to say that this relative offset, this chunk of memory on disk is going to be mapped into memory at relative offset 610. I could also put it to VA. And then it'll combine the base address plus an RVA, and it'll say, okay, the base address for this module was, the image base was 10000. The relative virtual address of this particular, structure is 610. So add the base plus the RVA, and this is the absolute virtual address. So I would have put this in RVA mode, I guess, for now. Because, like I said, each of these things is trying to say there's some relative offset into memory once this thing is loaded into memory. All right, so we're at the first image import descriptor thing, so I'll just call it an import descriptor. And I said there's going to be an array of these structures, and the way that you know how big the array is based on, back in the data directory, there was that virtual address saying it's at offset 610, but its size hex 28. And so adding this up, it should be, was it 28 or 24? I think it's 24. No, 28. And starting at 10, ending in 38. So total 28 bytes, hex 28 bytes. It's terminated with a null entry where they just filled everything in with 0. And so what this is saying is null.sys imports functions from exactly one module, ntus kernel.exe. And so basically, at load time, the OS loader would go in here and it would find this table and it would say, okay, I see that you need modules. I see that you need functions from ntuskernel.exe. I will see if I loaded ntuskernel.exe already. It will have, because that's the first kernel module that it loads. Right? The kernel loads first. So it'll say, okay, it looks like you need NTOS kernel stuff. Looks like I see NTOS kernel in memory right here. And then the OS loader is going to go out, and it's going, well, first it's going to go to the import names table. And so we go to the import names table. It's at offset 638. And I can see it called right here, import names table. Question or no? In your head, you know. At offset 638 into virtual memory, I have my import names table. And this was that image thunk data thing, which can have 4 possible interpretations. But right now, because it's an import names table, it's only going to be that interpretation where it's pointing at something, which is going, when you go to that location, that something is going to have the hint, and then it's going to have a string. So the literal thing, so this is definitely where it starts getting a little hard to read the P view thing, but it's saying at RVA 638 into memory, the literal value right now is 666. That's an RVA which is pointing at some data structure. It's that, I don't even remember, there's so many names. It's that image import by name data structure. It's this middle column in this thing. So this right here was filled in with 666. The next one was 67E. Right. 7E. Next one was 696. Right? And each of those is a relative offset saying this points at some other structure, this image import by name structure, right? And so in order to find that, now I need to go to offset 666 and offset 67A and offset 696. And so if I go into those, so what it's trying to do right now is it's trying to, like, you know, help you out and say, oh, you don't really need to go look this up. I'll tell you, it's just going to be hint 14B and string IO delete. But if we want to actually literally go look at it, then there's this thing right here. You know, we can see that if this is 666 and if this one ends in 650, it should be like probably pretty close to right after it. So right after it, there's just this big array of hints and names, and they're all just blobbed together because these pointers are going to point at some offset into this thing. So right here, this is 664, this is 665, and then this right here, this 4B is 666. So it's so it's little endian, it's a D word in little endian order. So you got to flip it around. It's 0, 1, 4B. That's the hint side. That's telling the OS loader, hey, go check the export table at index 14B. Maybe that's where you'll find, you know, IO delete symbolic link. Right? So immediately after are the ASCII characters, you know, IO, D, E, etc., ending in null characters right there, right? So you can see this is the sort of data structure where initially the import names table points here and the import address table points here, but eventually we flip over the import address table and fill in real function pointer absolute virtual addresses. But for now, if I'm looking at it on disk, both of these things point here. So to try to, you know, justify that claim, and to justify the claim that the import names table is different from the import address table, we go back up to the directory thing. So back up to this, you know, array of descriptors here. So the import names table that we just looked at started at offset 638. And that was the original first thunk sort of data structure, right? The first thing. Down here, this was the first thunk one. And it's saying this starts at offset 300. So this is relative RVA 300. So yeah, those are clearly in different areas of memory. So offset 300, if I go up here, this import address table, which it's helpfully telling me at offset 300 right here, is the import address table. And so if I go up there again, I have the same literal values. So initially, right, so initially, well, that's in memory. So this one is 66. 7E. Right, so initially these are all the same. So now the thing is, since I'm looking at a kernel module here, I can't go in with, well, can I? The local debug? Let me try something here quick. I don't believe I can go in and show you the actual import address table things with the local local kernel debug session, but maybe I'm wrong. So let's see quick. All right. H. Okay, bear with me for like 1 minute here. I just want to see if this is even possible. All right, well, I'm going to wait until I do it with the user space thing because I kind of have a feeling that this is not going to work. So I know it's going to work with user space, but I will delay gratification. All right. So anyways, what I wanted to show was, he's getting filled in with the absolute virtual addresses, but we'll show that with user space stuff. So anyways, though, this was the first simplest possible example, and null.sys imports only one module, NTOS kernel.exe. Right, and so we went through all of this within PEview, but just have that there. All right, so here's a slightly more complex example. This is beep.sys. This is the thing like that gives you that annoying, really loud beep that doesn't care about how you have your volume settings. So this one imports functions from two modules, NTOS kernel.exe and HAL.dll. HAL is the hardware abstraction layer. And so now we have slightly more complicated, and now this is just to show you, this is not full. There's more than 3 things that this imports from NTOS kernel, or HAL rather. But this is to show you roughly how stuff gets spliced together, right? So because beep.sys requires modules from requires functions from 2 different modules, their tables are all contiguous. But these offsets, these RVAs for the original first thunk and the first thunk, these are just, offsets into some larger table where there's going to be a bunch of entries which are for NTOS kernel and then a bunch of entries for HAL.dll. And the thing which I had forgotten last time is, the question is, how do you know how many entries are for HAL.dll and how many are for NTOS kernel? It turns out you terminate them with a null entry. So there will be, however many things for HAL.dll followed by 0. And then, the pointer for NTOS kernel will point into the next entry. Then there will be however many entries followed by null. So If you want, you can go open up beep.sys instead of, so this is, just showing the exact same thing but with two tables basically together saying, on disk, they both point at this image import by name structure, which has the hint and then the string. So, but in memory, it's going to, the import address table is going to be filled in with some absolute virtual addresses.
Okay, good. I'll take it
So,
a little farther
if you
away
want to
from my
look through
face. Sorry about
beep.sys
that.
quick,
Just a thought. If there was kind of like a little roadmap, or not a, God forbid, I
so
should
how do we
mention the
get
word
to the
flowchart.
import?
But
All right,
if
someone
there
else
was a
tell
little
me. How
flow
do we get to
diagram, almost like a pointer diagram, to kind of
I
work
think we're
way
calling it
down.
import directory table in here, but
After I
like
take this
expand everything
class,
and find
I
it.
would like
How
totally
do I
remember that
walk
because
the
I can
data
go back
structures
to
in
it.
order to get
Because
the right
I know about
offset
inodes and other
for
things and
the import
Linux and different data structures, but Windows blows me away.
Where should I go first in order to like wind my way over to the import information? Section init? No, that's cheating. Starting from the DOS header. Right, so the DOS header, okay, I'll do the first part. The DOS header, so here's what I'm looking for basically. The DOS header, right, it says, the last entry gets me to the NT header, right? From the NT header, where do I go? Optional header?
Okay, I can grab it. No, I can go to the first slide. I've got the slides up right now.
Yes, I do go to the import table. This one called the import table, this is actually a data directory entry, so that last 16
it just helps me hold it together,
header, those are
sort
each
of
entries into the data directory table.
I may be
It's just
alone,
an array of these
I'm going to
RVA
take up
sizes,
the
right?
class time.
So I go to that import entry for the data directory, and then where do I go from here? Right, so we go to the RVA that's listed for the virtual address within this thing. So that's the 880 field. So we need, somewhere within this file at 880, there's going to be some import information. And, we could, just go like this and see, oh, that's RVA 240, and then go like that, and that's 268, and that's 300, and that's 780, and then 780, and then that, and then there, and then that, and then there we go. So if I were to keep walking down every possible thing, eventually I would get to something that tells me I am RVA 880, and we know RVA 880 is the import information. All right, so if I want to look at the import names table from here, where am I going? Let's say I want to look at the import names table for hal.dll. Where am I going next? Yep, 8BC. The first thing that was the original first func sort of part of the structure. That's saying at 8BC, there's going to be an import names table. And that's going to be the entries for hal.dll. So 8BC right there. And so now you can see that key view is sort of breaking these up, and you can also see the terminating null character, or null
if you had something like that with less,
that was again
and you abstracted away a lot of the detail, then it would kind of lead me on a yellow brick road tour
table starts here,
of
and you
where to
just keep
find
walking
things.
until
That's
you
why
hit a null.
I didn't try to answer questions, because
this is an RVA of,
I got a little lost. Now
and,
that's me. That may not be the entire class.
Yeah,
I think
so
it's
this is
probably
the RVA
mostly
of a
me,
hint
but
and
you never know.
string. This is the RVA of hint and string, hint and string, hint and string. Eventually I get to a 0. Okay, that's all that there is. And so this is basically the OS loader's job, is just walk through these tables, find these things, go to the exports chunk. We haven't learned about exports yet, but you can have a general rough idea that there's just going to be some table somewhere that says my printf is at offset blah in my file. My mem copy is at offset blah in my file. Right? So, yep, that's double imports in beep.sys. Any questions on, okay, go ahead, but I can't hear you very well. Try again. Bill? All right, yeah. Now we're going to do, so now we're going to actually show what I was trying to want to show with kernel, and we'll do this and then take a break. Now we're going to play with WinDebug, and we're going into a live running program, and we're going to say, here's telnet.exe in PView, and here's telnet.exe running in actual program. And then you'll see the difference when you go to the, we'll walk through the RVAs and stuff like that, and then we'll see when we walk to the RVA for the import address table, then we're going to see the actual virtual addresses filled in. All right, so everyone, on your systems, go to All Programs and then Debugging Tools, and open up WinDebug. And so we're going to have to, this is going to take a little bit because we're going to want to get a common formatting view so that we're all seeing the same thing. Yeah, open up WinDebug, and then go to File, Open Executable. And from there, you're going to go to C:\Windows System32 telnet.exe. Also, you can open up telnet.exe in your PE view as well. So just go ahead and hit OK and let it sit at this prompt. Fine for now. Let's also open up PE view or let's open up telnet in PE view. Again, C:\Windows System32 telnet.exe. All right, so right now you should have telnet.exe open in PView, and then you should have also opened it in WinDebug, and it'll just be sitting at this prompt asking you, would you like to save your thing? All right, at this prompt for saving your workspace, say don't ask again, and then hit yes. All right, so what it does then is it starts executing telnet.exe, and it loads a bunch of the modules, and then it eventually sets a breakpoint. It breaks at an early place, but not immediately. So it's not immediately, and it's not breaking at main. It's just at some predefined breakpoint within it. Well, NTDLL debug breakpoint. Okay, so this is where we have to all get on the same page in terms of displaying all the same registers and stuff like that. We're going to do it the same way that we did in the intermediate class for people who've taken that already. But for this initial window, well, let me say something about this first. Right now, we actually are seeing the memory map as it exists when this breakpoint got hit. So telnet.exe got loaded at virtual address 100000, and it has a size of, 30000. So it's starting at 10000. The size of image was 30000, and so it's taking up that space. So roughly speaking, Bill, if you could come over to the board. Just going to give a rough notion of, this is sort of like we saw in the OS loader picture with the squiggly lines and stuff like that, but roughly speaking, what we're going to see here, I'm going to do again as I normally do: low addresses low, high addresses high. So roughly speaking, what I should see is, this is telnet. Telenet, is it? Telnet. Right? And this is address 100000. How many zeros? 6, 2, 4, 6 zeros, and a 1 and a 0 in front. Right? And then this last address of telnet is 010. Well, it's not actually the last address. Is it? Yeah, it's 3, but it's technically considered the last address. I think it is. How many zeros after it? 4? Right? So this is saying telnet is here, but then we've got all those DLLs way up higher bordering on kernel space. So in Windows, kernel starts at 8 and 7 zeros. Right? That and above are kernel, and 7FFFF and below are user space. This is just by the convention that they happen to choose. On Linux, I'm pretty sure it's backwards. Low addresses are kernel, high addresses are user space. Right, so, but somewhere up here in this address space we've got, let's see, are those ordered correctly? No, they are not. So, that one is the highest though. No, it's not. 7E41. Right, so somewhere around 7E41 is zeros. What is that module up there?
That's user 32.
All right. All right, and then somewhere below it, I've got, let's say, ntdll.dll. I'm not going to exhaustively put these in. Can someone read out ntdll?
It's 7C950. That was NTDL.
Right. So the point is, I've got a bunch of modules in this guy's address space for Telnet, right? Each of these modules can be mapped into one copy of physical memory, and they could be shared amongst many virtual address spaces. So this virtual address space is, Telnet space. Right. But over to the side, we can have, calc.exe space. And see, calc.exe would similarly think that it has this 4 gig range, over all of memory space. And, calc would get here, and then, ntdll would be here, and stuff like that. So these could be sharing the same sort of information between them, except the only difference would be, they've got different executables, potentially mapped at the exact same addresses, but these are different memory spaces, and it's the kernel's job to keep these things separate, basically. So all the kernel space is all the same amongst them, and they can't write to it because we've got memory permissions and stuff. But the point is here, this is roughly speaking what we're seeing at this point. And so remember, there's this import table somewhere in telnet.exe, and the whole point of the import table is just to say, look, I need to call a function out of ntdll. So there should be a function pointer here that points somewhere in there, and then there's another function pointer here that points somewhere in there, and then there's another function pointer there that points somewhere in there, etc. So the whole point of the import address table is saying, I've got all these other modules that I want functions from, and it doesn't need something from all of them. Like this one may only be there because this one wants to call it and stuff like that, right? So these are all the things which Telnet depends on and which are prerequisites of the things that Telnet depends on. They're all loaded into the memory space. But at this point, this is not exhaustive, actually, because some more stuff can potentially be loaded. Yes?
Practically speaking, when a system boots up, are these DLLs generally going to get loaded in this order, and they'll generally be in about the same regions of physical memory?
Well, in terms of being in the same regions of physical memory, I'd say probably. In terms of virtual memory, there's no reason they need to be because of things like ALSR and stuff like that. But yeah, strictly speaking, if the system is deterministic and if the same things are being loaded in the same order every time, these are user space, but for the kernel modules, right? So NTOS kernel is the first thing loaded, and then NTOS kernel wants hal.dll, and it also wants, bootvid.exe or DLL, whatever it is, bootvid.sys, I think. And so anyways, of those kernel modules and stuff, right, assuming it loads everything in the same order, they're all going to be mapped roughly in the same space, except not entirely, because like I said, in kernel space, it doesn't, for instance, care what you ask for, and there's a little bit of randomization even in XP, so it's not strictly speaking randomization, but. Okay, so anyways, the point is right now, we've got telnet.exe, we've stopped at a breakpoint. The OS loader has loaded a bunch of these modules. It's loaded telnet. And I believe right now that it's actually loaded, it's actually filled in a bunch of the import address table. So theoretically, we could set a breakpoint early enough. So if I was doing kernel debugging, I could say like, dear kernel, stop immediately when telnet.exe is mapped into memory, but the OS loader has done nothing to it. In user space, I haven't got around to figuring out if there's a way to like stop it before the OS loader does anything. But in kernel debugging, it's very easy. But from user space debugging, less so. There is technically a way, I just didn't get it to work last time I tried it. So anyways, at this point, the import address table has been filled in with some of these addresses here. And so what we're going for with this little lab here is we got telnet.exe and PE view. And so we're going to go look at the import address table in that. And then we're going to, or import names table and address table in PE view. And then we're going to look in memory when it's actually mapped into memory. What does the import address table look like? What does the import names table look like? I'm claiming that the import names table always looks the same, and it's only that import address table that gets filled in. So see if we can validate those claims. So, but we need to organize our windows and stuff. So you can see that I can like drag my window with the white background around. I want to drag that entirely over the, so that it looks like it's going to fill the entire gray background window. When you do that and you drag it in there and you let it go, now when you expand the window, it should be expanding the entire window. It should take up the entire WinDebug screen. And then I'm going to just start splitting this off so that I don't have to use a bunch of commands. So, for instance, if you hit Alt-5 or you just look at, you mouse over to find this little thing that says memory window, hit that memory window. It'll pop up another, hovering window. But what I want you to do is move it around until you can pull it to the top so that it splits the screen and it takes the top half of the window. So it should look roughly like that. Yeah, and sometimes you may have to drag it somewhere off to the side, let it go, and then drag it back because it won't, find the right place and stuff like that. All right, let's see. For purposes of this lab, do I have to do anything else? Do I need registers? I don't think so. All right, I'm going to try it just like this, and we'll see what we can do. Well, first things first. We know that telnet.exe is based at this virtual memory address, 100000. If I take that address and I copy it and I paste it into the memory window, I should expect to see an MZ as the first 2 bytes, right? I'm saying this is the very base address of where this module is loaded into memory. The very first thing that I should ever see in a PE file, the headers get mapped into memory as well. And so, indeed, when I put that in here, what I'm seeing now is telnet.exe's, DOS header, stub DOS program. Right there, I can see the little PE, right? So that's, where is it? Right about there. That's that 4-byte signature, I think, in middle endian order. Right, that's the signature, and then there's like, some chunk of this is going to be the file headers, and then some chunk of this is going to be the optional headers and stuff like that. And then we got section headers. I can see like .text, .data, .resource. That means this, stuff around here must be that array of section headers. So anyways, now this is really where we have to start actually interpreting RVAs and stuff like that in order to figure out how the heck we're going to find that import address table. So I'm going to go back up to this. Go back up to my base address. I am going to guesstimate the offset. Well, actually, I don't have to do it. I can cheat and use the telnet.exe in PView, right? So that was the point of opening this. All right. So if I open this, and I'm going to now just cheat and skip directly to the import directory table. And if I use PE view, and I use that little RVA arrow as before, I click the RVA arrow, and it now has this column set as RVAs, and I'm clicked into the image directory table. These are all the modules which telnet.exe imports from: MSVCRT, Microsoft Visual C Runtime, Advanced API 32.dll. These are all the modules which this telnet.exe imports. And so what I'd like to now just see is, okay, well on disk, I know that the import address table is pointing at those same structures and stuff like that. But let's find like one entry in the import address table and see what it looks like on disk and then see what it looks like in memory. So this is saying at, offset 1234, conveniently enough, into telnet.exe, I will have the beginning addresses for MS VCRT. So 1234 is probably 2 right there. So that's 10000, right? 1, 2, 3, 4 is down here. Scroll down to right there. All right, so these are the functions which are imported from Microsoft C. So offset RVA 1234 into this file. Then you'll see these things, and they look like common sort of standard C library things like exit, A2I, to lower is alpha, SN printf, here's printf. I may not call it printf, so that's printf. All right, so right now, I'm just going to take the first one. 1, 2, 3, well, I'll take the second one. 1, 2, 3, 8. We say this points at 2W lower, right? Now, right now on disk, the literal value in this array, this is, those arrays to the side. It's the array to the rightmost side. When we have those pictures of 2 arrays pointing in the middle, the rightmost one was the import address table, right? And we said initially it points into the middle, into those hint and then name things, and that's what it does right now. And so what this is saying is relative offset 1238 into this thing when it's in memory should be the address of 2W lower. On disk it's not, but in memory it should be. So if we go into WinDebug again, and we just take that address in memory that we have already, and we just do plus x1238 like that, then what we're seeing now is actually this data value in, this is the actual import address table value. So I'm going to change over my view. So instead of looking at it in bytes, I'm going to look at it in long hex, so 4 bytes at a time. So if you change that to long hex, you've got your virtual address set to your base address plus the RVA 1238. What you see is, this now is not the same thing as is on disk, right? On disk, you have the literal value 0000D88C. In memory, you have the literal value 77C1 blah, 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 blah. So as you can see, these all look like they're roughly in the same memory range because they're all just pointing into functions in the C runtime. And so if I really want to prove that these, look like there's some function addresses, what I can do is pull up the disassembly window. So if you mouse over to this thing with the little 1.0 in it, or you hit Alt-7, click that and you pull up the disassembly window. And I'm actually going to split the bottom window now, like so. I'm going to split the bottom window, and then I'm going to copy the address out of the import address table and just put it into the disassembly table. And you may have to delete the last character and then retype it. So again, copy this 77C1D7B7 out of the import address table, paste it into the disassembly window, maybe delete the last character and retype the last character. And then now what you'll see is, yes, indeed, starting at the address 77C1D7B7, that is the first instruction of MSVCRT 2W lower. Right? So what we saw here is that in the, well, I'm going to stop talking as I wander around. Make sure everyone's got that. Does everyone see the actual assembly code? Yep, yep. Right, so what we saw here was that indeed, in memory, the import address table is getting filled in by the OS loader with real addresses of function pointers. So somewhere, in one of the somewhere in telnet.exe, there's a call to W lower, right? And that call is going to be a call to this address, 1001238, right? So like we had seen way back with that, let me pull all the way back to, like, this one right here, right? Oops. Right, this was just some random hello world thing. Hello world happened to be based at 40000. If we were looking at telnet.exe, we would expect to see there would be a 1001238 right here. And it would be saying, go to 1001238, pull the memory out of that, that's that 77 whatever, and call to that function. And that's how you would call to whatever it was, to lower W, W lower. Yes. Right. So that was that's the basics of showing the discrepancy now between on disk import address table and in memory. And so the one other thing I want to show just quick is that still in memory, the import names table still points at those structures which are a hint and then a string. So going back to pview, we could go back to the, say, import, just click on the import names table to pick something randomly. We'll pick the very first thing. And it's saying, you know, D438 into my binary in memory is the first import names table thing. So if I go to well, I'm even going to skip that. Well, no, I'm not going to skip that. If I go to D438 in memory right now in telnet.exe, if I go that much offset into telnet.exe, I expect to still see 0000DA12. Right? So if I go back here, and I go whatever this is, D438, D438. There we go. I've still got the same import names table entry. And that import names table entry, if I grab that RVA, copy that, and I pull that over to right here, then what I see is it's going to be, well, it's hard to see it that way. Let's put it back to bytes. I'm going to have 2-byte hint, right there, followed by a string. And so I got 2-byte hint, 01FD, followed by a string, which is reg set value XW. Right? Yeah, I changed it back to bytes. Because otherwise the little endianness gets messed up. Right, so this is just saying the import names table is all the exact same RVAs and everything that it was on disk. You still use those same things to find it in memory. And the import address table is going to be, you know, you'll use the RVAs to find the import address table, but then ultimately the values there, that entire side array gets filled in with real function pointer addresses. So, all right. So that's our import names table. That's our import address table. That gets filled in by the OS loader when something gets moved into memory. Yeah, we're going to take a break. I took you quite a bit over that time.